Hi everyone. In this last segment on optimization, we're going to take a look at a few more types of problems. This one happens to be a cylinder problem where we're going to try to minimize the cost of producing this cylindrical can that can contain an amount of liquid. Typically this is like a Coke can, right? Or any soda can like that. It can contain 355 milliliters, which is the same as 355 centimeter cube of liquid. And so what should the dimensions be in order to end up with a cylindrical can with the lowest possible cost? So that is our question. And then we're going to do a couple more variety questions in this segment, but it is impossible for me to cover every single type of optimization problem in these videos, but I'm trying to give you a solid foundation. If you understand the technique and you can do, a few of the basic types, I think you can extend that to many other types of problems as well. So because we're dealing with the volume of a cylinder here, it's worth reminding everybody what is the volume and what is the surface area of a cylinder. So while volume is going to be area of the base times height, base is circular with a radius of r, so the volume of a cylinder will be area of the base, which is pi r squared times h. On the other hand, surface area is more complicated, okay? Surface area is you have a top circle, the bottom circle, and you have the side panel of the cylinder. And if you cut open the side panel, if you cut it from here and open it up, it actually turns into a rectangle, okay? So you have really a circle, and a rectangle for the surface area. So that's what we have, two circles and a rectangle. The circles are of radius r, so pi r squared plus pi r squared, which will be 2 pi r squared. And the rectangle, you see the length of this rectangle comes from this circumference of the circle, right? So this, when you open it up, this circumference becomes the length of the rectangle. So that's 2 pi r. And the height of your rectangle will be the height of your cylinder, which is h. So if you multiply those two dimensions, 2 pi r times h, that is the surface area of the side panel of your cylinder. So if you add up everything, pi r squared plus 2 pi r h, it will be 2 pi r squared plus 2 pi r h. That is the surface area of a cylinder. So for this question, if we want to use the least amount of aluminum to create the can, we need to minimize the surface area. Given volume is equal to 355. So let's write down what's given and what we're supposed to determine. So minimize the surface area, and surface area formula we just got, 2 pi r squared plus 2 pi r h. Given that volume equals 355, and remember volume is pi r squared h, and that's equal to 355. Now, which one of these are we supposed to minimize? I already wrote it here, of course, but notice that one of them is your constraint. One of them, you have an equation on one side, you have a number, on the other side you have variables. The other one is just an expression, right? It's just a function you're trying to minimize. It's not equal to anything. It's not equal to a number. We are just trying to minimize that and figure out what r and what h would minimize. So as with all optimization questions, use your constraint equation to write one variable in terms of the other. So if you look at this equation here, 355 equals pi r squared h. Which one will be easier to solve? H, right? H equals 355 over pi r squared. And once you have that, plug that into the equation above, the one you're trying to minimize. So right there where you see h, instead of that, go ahead and plug in 355 over pi r squared. So if we do that, we're going to get surface area equals 2 pi r squared. That part doesn't change. And then 2 pi r times h, and instead of h, I'm plugging 355 over pi r squared. And we've seen examples like this where we understand it's easier to simplify this first as opposed to trying to use like product rule or the quotient rule to differentiate, right? So notice first of all, the pi's can be canceled. Then r over r squared will leave an r in the denominator. And don't forget to multiply 2 times 355 to get 710. So this is our surface area equation in simplified version. 2 pi r squared plus 710 over r. Now we're ready to differentiate. So the remaining steps are going to be pretty much similar to all the other problems we have done. The beginning was a little bit complicated because we had to understand, the surface area of a cylinder and so forth. But now that we have our surface area equation in one variable, so what we're supposed to do is differentiate it with respect to r. And as you do so, the second term, it would be helpful to write it like this. 710 times r to the negative 1. So you're going to bring the negative 1 down and subtract 1 from the power to differentiate that term, right? And the first term, notice 2 pi is just a number, it's a constant. It will remain as such. Just differentiate the r squared. So you bring the 2 down and subtract 1 from the power. So there you can have 4 pi r. And over here you can have negative 710 r to the negative 2. Which can be written as negative 710 divided by r squared, right? Because r to the negative 2 can be brought to the denominator. So I'm setting this equal to 0 because as always, I'm looking for points where slope equals 0. So those are the points, hopefully, that will pinpoint to us where the minimums are for this question. So now to solve this for r, I'm going to add 710 over r squared to both sides. So it appears on the right side. Multiply both sides by r squared. So we'll have, so on this side, r squared will cancel. On the other side, r squared times r will be r cubed. So you can have 4 pi r cubed equals 710. And what do you think we should do to solve for r here? If you said let's first isolate it, you're absolutely correct. Divide both sides by 4 pi. And what do you think will be the last step? If you said take a cube root, once again, that sounds wonderful. Indeed, we need a cube root to solve for r. And the only thing about this is when you're entering this into the calculator, be very careful, especially if you have the older version of the calculator. When you enter 710 over 4 pi, put the 4 pi in a set of parentheses so that you're dividing by the entire quantity. Otherwise, it will divide by 4 if you don't put the parenthesis and multiply by the pi. And to take a cube root, whatever answer you get, raise that to the power of 1/3. Or you can use the cube root symbol hidden under your math menu. So if you do that, you will get r equals 3.84 centimeters. Okay, and once we have r, we can go back to one of our earlier equations over here. H equals 355 over pi r squared. So go ahead and plug the value of r in there and square it and evaluate h as 355 over pi times 3.84 squared. And once again, as you're entering this into the calculator, if you have the older operating system, it would be helpful to put a parenthesis for your entire denominator. So after 355, division sign, open a parenthesis, enter this product, pi times 3.84 to the second, and then close the parenthesis, and you should be able to get 7.66 centimeters. So that means the dimensions of the cylinder, we need really r and h. R is 3.84 and h is 7.66. And for this question, they did not ask what is the lowest surface area to create such a box that can contain 355 milliliter of liquid. But if they did ask us, we would have to come back to the surface area equation over here. So pick maybe the one that looks the easiest, perhaps this one, 2 pi r squared plus 710 over r. And there you will plug in your r value to find the minimum surface area. And how do you check the answer? I would go back to surface area prime, take the derivative one more time to get SA double prime, and then plug in your r value, confirm that SA double prime is positive, which means concave up, which means we do indeed have a minimum. Okay, so that is one more type of problem that we have seen, including a cylinder. And the last type of problem I'd like to go over with you is something we've seen at the very beginning opening lesson on optimization, a very unusual problem, but also a very interesting one. So you have an island and you're trying to lay pipe from the island to a power station, which is 10 kilometers rather, down the shoreline. So the question is, where would you draw the pipes from the island to the shore, given that to put pipes underwater is more expensive? It's 2-to-1 ratios, $2 per meter to go underwater versus on land is $1 per meter. So the question is, where would you put it? Like from the point, let's say we call this point P. So how far down the shoreline? Is it 5 kilometers, 4 kilometers? So where would you put it? If you call this X, what is X? So that the total cost of laying this segment of the pipes and this segment of the pipes, the total cost is as low as possible. So for this question, it will be helpful, first of all, to write down the cost equation. Okay, so we're calling this side X. Oh, actually, I changed it a little bit, so I'm calling this corner point O, and the point where you're going to connect the wires or the pipes with the shoreline, I'm calling that point P. We don't know where it's going to be. I'm just calling, so it's X units away from the origin. Okay, now we know that the island is 4 kilometers from the shore. Direct distance is 4 kilometers from there to there. So that is the fixed length. I can put that in as 4. And think of this, no matter where you connect that line, it's always going to be a triangle that is being formed, right? A right triangle. So what will be the hypotenuse of that right triangle? The hypotenuse will be sum of the square root of the sum of the squares of the legs. So that will be the square root of 4 squared plus x squared. And 4 squared is 16. So the length of the hypotenuse, the part that is going underwater, is the square root of 16 plus x squared. Now let's not forget the cost, okay? So the cost of going underwater is $2 per meter, and per kilometer that is $2,000 per kilometer. And on land, the cost is $1 per meter, so that's $1,000 per kilometer. So what is the total cost of laying this segment plus this segment? So this segment that goes under the water, the length is square root of 16 plus x squared, and the cost per unit is 2,000. So let's multiply them. 2,000 times the square root of 16 plus x squared. Okay, and the other segment, the one that is going on land, the wire, that is going to be, the length of that is, first of all, since the entire distance from the point O to the power station was 10 kilometers, and since this distance is x, this will be 10 minus x, and the cost of that segment will be, since on land the cost is $1,000 per kilometer, multiplied by 10 minus x. Okay, at this point, we have the cost equation, and luckily it's in one variable only. And I'm just going to distribute my 1,000 in the second portion of the equation. So 1,000 times 10 is 10,000 minus 1,000x. And next we're going to take the derivative of the cost equation. This is where we have to be careful. The last term will be super easy, right? It's just negative 1,000. The middle term is super easy. The derivative of a constant is itself. But this is the part you have to be careful about. How do you differentiate the square root of 16 plus x squared? Well, think of it as 16 plus x squared to the power of 1 over 2. And you can bring the 1 over 2 down, subtract 1 from the power, and so that will be negative 1/2. And by the chain rule, multiply everything with the derivative of the inside. Okay, so that's how you can find the derivative of 16 plus x squared. And because the 2,000 is a constant multiple, that can stay as it is. Now we differentiate the square root term. That's exactly what you're going to get as I did on the right hand side over there. And -1/2 power means bring it to the denominator as a square root. And remember, the middle term disappears and you have -1000 at the end there. So as we simplify this a little bit, the 2's can be canceled. And don't forget to set the derivative equal to 0, right? Because we're looking for where tangent lines are horizontal, so we can find maximums and minimums. So when you set equal to 0, you're going to have this equation. 2000 times x divided by the square root of 16 plus x squared. And let me add 1000 to both sides of the equation, so equals to 1000. At this point, I'm going to divide both sides by 1000 to make the numbers a little bit smaller. So all we have is 2x over the square root of 16 plus x squared equals to 1. Remember, I divided both sides by 1000. Numbers are smaller now. And to solve this equation, I'm going to multiply both sides by the denominator. So 2x equals the square root of 16 plus x squared. And to get rid of the square root, I'm going to square quantity both sides. So 2x quantity squared is 4x squared. And on the right-hand side, you lose the radical. So it'll be 16 plus x squared. And finally, to solve for x, let me gather the x's on the same side. 4x squared minus x squared on one side, 16 on the other side. So if 3x squared is 16, divide by 3, right? X squared equals 16 over 3. And final step, how do you solve for x here? Take the square root, right? Take the square root of both sides. Now the square root of 16 over 3 is square root of 16 over square root of 3. Square root of 16 is 4. So you're going to have 4 over the square root of 3. And you can get that as a decimal if you like. That's approximately 2.31 kilometer. So what we're saying is for the optimal solution, we should connect the wires at 2.31 kilometers down the shore, something like this. And the rest of the way, we should go above ground. The rest of the way. So about 2.31 is where we should connect it. That's what we're saying here. Now, to check our answer, we're going to do something interesting here. Instead of doing second derivative, what we're going to do is we're going to look at the endpoints of the domain. Okay, that's how you can find maximum, absolute maximums and minimums, right? And think about the possible values of x. Okay, if you go directly down the line here, x would be 0. That's one possibility, right? Or if you go all the way extreme this way, everything under the water, x would be 10. So the lowest x can be 0, the highest x can be 10, and the relative minimum that we found is 2.31. The critical value is 2.31. So let's put all of those on a chart and plug them into our function, the cost function, which was this. So if you plug in a 0 for everywhere you see an x, you're going to get a total cost of doing this, laying this wire is $18,000. If you plug in 2.31 into your cost equation, you're going to get $16,928 approximately. And if you plug in a 10, the other endpoint of your interval, you're going to get, plug into the cost function, 21,540. Which of these is smallest? Clearly it's this one, right? The smallest cost value. So that's where the absolute minimum occurs. And so we can confirm that the point we obtain indeed makes the cost function a minimum. We even show this an absolute minimum in this case. So that would be the way the engineer should design the project to end up with the lowest possible cost. So now I would say go back to your assignments, your group activities, and solve as many questions as you possibly can. And that's truly the only way to master these questions. And yes, these questions are a bit complicated, but you know what? Computers still cannot do word problems. Computers still cannot do optimization, reading a text, converting into an equation. Yes, they can solve equations. Yes, they can take derivatives, but this is worth your time because you're using your brain at a high capacity and you're doing problem solving skills, something, there's a very high level function, and it's very, very good for you to get better with problem solving skills and to develop your skills in areas where computers are not very good yet. All right, so enjoy the section, and don't get discouraged if you cannot do it right away. be resilient. You know, sometimes these questions will take a long time to figure out. Everyone that you get correctly, celebrate, because they are, clearly this is a challenging section, but I know you can master it with when you put sufficient time, and when you can do repetitions. Take the same type of problem, can you do 2 or 3 of them, and then move on to a new type of problem. Okay, so good luck. And if you have questions, please send me an email, post them in the discussion board.